Oh, okay. Oh, that's possible, something. There was a green box around it before. So. Okay. So we're not going to be using interferometric data in isolation. You're going to want to put this on city maps, fault maps, grounding lines. Also, you need to bring all these different data sets that is of use for your application into one sort of common reference. And the most common way of doing it is putting all this in a GIS system. GIS system is nothing but a common sort of a reference system that you can bring in all these different data sets and combine them, do intersection union operations on them. There are plenty of tools out there. The most common among geologists and geophysicists is GMT. Then there's GDAL, which is what we're going to talk about today. Then there's QGIS. If you can afford ArcGIS, I'm very happy for you. Most people can't. So QGIS builds on GDAL. Then there's Proj4 and PyProj, which is a library for doing projections. And there's a number of these tools. They're not exclusive. You can use them based on what you want to do with the data. There's Fiona, there's Cartopy, there's Basemap, all sorts of stuff. So when we talk about geospatial data, there's basically two types of data, raster data and vector data. When we did all this interprogram processing, these are basically 2D arrays. They are, so these are raster data sets that we generate out of ICE. Vector data sets are more like GPS stations or polygons or shapefiles. We're not going to focus on vector data. This tutorial is focused on raster data to help you work with ICE data sets and combine it with other external data sets. So like I said, there are plenty of GIS tools out there. Why GDAL? You don't have to. If you can make things work in other GIS systems, feel free to do so. The biggest thing GDAL is it's free and open source and has a large developer community. They're very active user lists. Over the last year, we've been working with them. We've gotten a lot of features we want implemented by them. We've contributed features to it. So they're very responsive. Then there's the other thing, which is I can do pretty much the same stuff from command line or from C++ or from Python. I don't have to remember too many different interfaces. It's also kind of the default backend if you're working with large geospatial data sets, like Google Earth uses it under the hood. Most people use GDAL under the hood for serving out geospatial data. So it's a good idea that if those people are using it, you might want to at least consider it or look into it for your own applications. Then there are extensive test suites, which is a good thing. So bugs often occur, but they get caught fairly quickly. And the other important thing, which I'm not going to talk about today, is GDAL not only supports raster data sets, it also has extensive support for vector data sets. So I can combine these two really easily. So it's sort of a one thing that serves most of your needs. Shapefiles to KMLs, and you can, if you have shapefiles and you want a raster image out of it, you can convert that. And if you have a raster and you want to create a shapefile out of it, you can do that. So those are fairly common applications that crosses both domains. So the thing I want to talk about first is the data model in GDAL. I think this is the strongest aspect. So they clearly define what they mean by raster data and what a specific raster data interface should look like. They don't care about the format. It could be PNG, GeoTIFF, NetCDF. Pick your favorite format, but this is how the data should be laid out, or this is how the data should be exposed to the user. So we'll just walk through the raster data model. I have the link for them, for it online. You can look it up. Oh, they may be updating the website. I'll try to get that going. Okay, I'll update the link. You should be able to do Gdal raster data model. So, okay, they made it explicitly raster data model. Okay. So the first thing the Gdal raster data model says is one data set can contain multiple bands. It need not be a single band. If you're working with optical imagery, you've always sort of do 3 bands RGB. If you're doing Landsat, you have 8 bands. But for a data set to consist of multiple raster bands, they should be of the same size. That's a requirement. If you have you're trying to do 2 physical quantities in the same file, but they're not same sized arrays, they should be treated as 2 different data sets. They are not one data set. And these arrays should represent information from the same point. So they can't just be 100 by 100 arrays. They should be from the same point on the ground. They should be co-registered. Only then can you consider these layers as bands of the same data set. Again, they allow these bands to be of different data types. So one could be int, one could be float, one could be byte. But there are some formats which allow you to do this, and some formats which say all bands should be of the same data set. They don't impose a restriction on this. But the size and the collocation is imposed by the data model. So one way of figuring out how many bands are there in an image is this simple command line utility called Gdal Info. This is pretty much the first thing anyone runs when somebody throws something over the wall, and you're like, oh, I have data over this area. Here it is. And they send you a file. You're like, I don't know what it is. There's no description. The first thing you do, typically, is run Gdal Info on it. We're going to do this on our open topography tile that we just downloaded. And it reports some really basic things. It basically says it's a GeoTIFF file, and it has size 3600.01 and 3600.01. Remember, Gdal establishes a convention. It's X followed by Y. The first number is the number of pixels in a line. The second number is the number of lines in the image, always. So everything, their map projections, their image projections, this is a convention. So stick to that. Then it reports the coordinate system. We will talk about this a little more in detail. It basically says it's in the WGS84 ellipsoid, that's lat lon. And then it says something about compression, and the type of data is float32. So if someone gives you an arbitrary file and says, use it with your data, and they don't tell you anything, this would be kind of the first thing to kind of discover what's the data with Gdal Info. Now, if you have done your linking right, if you noticed yesterday, there was a .vrt file associated with every ICE product. You could basically use Gdal Info on that file. So we had geocoded files with a .geo extension. They all came with a .vrt file. So you can run Gdal Info. Hopefully this works. And it should say, OK, you're pointing to a VRT. The VRT itself points to another physical file. And this is the size of the image, 2989 pixels, 3547 lines. It gives you the top left corner, what projection system it is in. And it says there are 2 bands in this image. The previous DEM was 1 band. We know our coherence correlation files that are put out by ICE are 2 bands. The first band is amplitude. Second band is the correlation. And the first band is float32, and the second band is float32. So this is the quick command line way of doing things. You could also completely do this programmatically within Python. So if I were to do this in Python, this is how I would kind of do it. I would import Gdal. I would open the file in read-only mode, and I would query it for how many bands it has and what is the size of it. So run the cell. If the previous command did not work, then you linked to the wrong folder. You did not link to the correct strip map app folder. In the notebook. Yeah, we made the link in the notebook, yeah. So everybody with me so far? Okay, so that's about the basic raster bands and the size of an image. Then there's data types. Your arrays don't have to be restricted by certain types. Gdal will support byte, int16, unsigned int16, int32, unsigned int32. The things that are of most interest to me, at least as a radar engineer, are the last 4 layers, which are typically not supported in most GIS systems. So Gdal has internal support for complex numbers. Cint16 means I can directly start using it with SLC products that are put out by most European sensors. Cint32 means I can even handle weird JAXA products. Then Cfloat32 is our standard SLC, and if you really want to waste precision and memory, you can do Cfloat64. You'll do that. Yeah. Yeah, go for it.
So you mentioned there are file formats that allow different. Oh, I just had one more quick question. What is ds equals none? Why did you put none there?
I see. So if you remember, like typical Python or MATLAB code, you open and you close.
Yeah.
Gdal doesn't give you a close. You just set the object to none, and it'll clear it for you. That's equivalent to file.close.
Thank you. I was going to ask you, you mentioned there are file formats that allow different types for different bands. What are they?
We'll have to look up specific formats, but I know I do it in VRT all the time. Like I would have an imagery layer, but my mask is a byte.
Right.
So I can put a byte mask as another band of the image with a floating point image or an int image. VRTs can let you do that. There may be other formats also. We'll have to go look up such formats, but it allows for it.
But it's not like BIL or BIP. It's because
yeah,
it's
those.
different.
So BIL and BIP are very specifically NV formats, and NV doesn't allow it. So BIL and BIP are not generic formats. They are specific to the NV format. And that's the origin of BIL and BIP, and they don't allow you to mix data types.
And BSQ?
All of those are specific NV types. They don't, BIL, BIP, BSQ have no meaning outside the context of the NV driver.
See. Okay. So in order to create different types for each band, what would you do?
You can have them as separate files and tie them in a VRT.
Oh, through VRT.
Through VRT. Or even if you write a raw binary with mixed types in it, in a VRT, you can say pixel skip is 8 bytes or 16 bytes. You'll have to build the VRT that way.
Quite versatile. Thank you.
Right. So if this were a VRT with 2 different data types, this band 1 would report one type and band 2 would report a different type on Gdal Info.
So it means all ICE products have like 2 bands raster.
Not necessarily. Most
Okay.
have one. Most complex images have only one band. There are some real valued products like unwrapped phase and coherence that are 2 bands.
That are 2 bands.
That are 2 bands.
So like if I want to work on coherence raster,
Yeah.
so I have to split the information like because I want to work on that band, specific band, right?
You don't have to split it. You can just do it programmatically by just We will get to that. You can read only one band. You don't have to read the other band in your programs.
So am I remembering right that the NumPy definition of, for example, C float 64 would be float 128?
That is correct. Complex 128.
Yeah. So they're got to be careful with that.
Yes. So when you do mapping between NumPy types and Gdal types, be careful. The C float 32 means complex numbers made of float 32. And NumPy calls it complex 64. And C float 64 is complex 128. But if you read it via Python this way, it does the conversion for you automatically.
Follow-up question. So would you still use ice2gis_xml.py to generate that different types of bands combining into VRT?
If you want to combine different bands, we don't know all your use cases. You might have to do some custom code to do that. Yeah.
Part of this training is to show us how to construct files with different bands and that kind of thing. So you'll be learning that. That's the purpose of this class. Any other questions?
All right. So now that we know Gdal supports complex numbers, let's go look at a complex value data we created yesterday, which is the topophase.flat. And if you run Gdal Info on it, it should basically say, we know topophase.flat was not geocoded. It was still in the radar geometry, so there's no map information associated with it, so it does not report any projection information. It just reports the size and the data type for you. And you could do the same thing programmatically. You could query, you can ask a file what data type you are. And in this case, we will do that on the GMT file in this case. Note that I'm using essentially the same set of commands for a geotiff or a GMT format, so when somebody says, oh, I gave you a file in this format, you're like, I have to convert it to use it in my program. If you just use Gdal consistently and the formats, you don't have to change your code. Just use Gdal to open it, use Gdal to read it. So we're going to do the same query on the SoCal DEM, and I made it print out the data type, and it says it's float 32.
Thanks. So when you're loading the Gdal datasets to process later on, you don't need to specify the file data type, unlike other programs. Yeah. So it just automatically recognizes what it is. Okay.
Yep.
Okay.
And what it does is it recognizes the internal data type, and when you ask for data, we haven't gotten to reading data yet. You'll see examples there. Basically gives you an NumPy array of the original data type. If your program needs another data type, in your program you do .us type something in Python. If it's the same type, it does no type conversion, but if it's a different type, it will convert. But the type conversion is something your program needs, and Gdal Python interface will essentially give you whatever data it is in its native format. So. Then the next important thing about raster data is the projection system. I know there's a few cryosphere people here who are used to working in polar stereographic. We did strip map and topsap using lat-long space, and if you are somebody coming from the optical community, or like what Gareth showed yesterday, you'd probably be converting things to UTM to do the modeling. So it's essentially the same data, just packaged differently on a slightly different map, and Gdal handles this support. So what is becoming more popular nowadays is these coordinate system representations can get pretty complicated. They're now the EPSG codes, which is a European Petroleum Standards Group, I think. It assigns a number to a specific coordinate system, and that sort of completely represents the coordinate system of the data you're in. So if you're giving somebody some data and you don't want to describe the whole, this is a Mercator this, or polar stereographic that, just give them the EPSG code, they know how to interpret your map data. We'll look at some examples of that. Also, I'd like to point out that there is this library called proj4, which is now kind of evolving into proj6, which almost all GIS systems use under the hood to convert projection coordinates from one coordinate system to another. USGS has its own collection of representing, own way of representing projection systems. It's basically an array of 18 numbers. You don't know which number stands for what. You can only basically use it with the USGS codes, so almost nobody uses it outside USGS. There's a more robust standard that's evolving. It's called by the Open Geospatial Consortium called OGCWKT. I think they have OGCWKT2 now that lets you talk about vertical datums, that has better support for vertical datums as well. That's kind of becoming the de facto standard for representing coordinate systems for maps. Like I said, EPSG code is the easiest to use. There's also, I mean, of course, Esri has its own coordinate system. They're a commercial company. So commercial companies tend to come up with their own representations. So these are all different ways of basically conveying to the user what coordinate system your data is in, or what is the north and east of a map that they're giving you. So we're going to see how GDAL can handle this information. So GDAL comes to this simple command line utility called Gdal Srs Info. It basically tells you, somebody told you this data is EPSG 4326, and you have no idea what EPSG 4326 means. You probably know some other convention, and you want to see what the equivalent representation is. You say Gdal Info minus O all. Basically, Gdal will convert that representation to all the different most commonly used things. So EPSG 4326 in proj4 means projection equals long-lat plus datum equals WGS84. In OGCWKT, EPSG 4326 means it is replaced by that entire string that basically describes every aspect of the coordinate system. Yep.
I didn't want to interrupt, but the questions I had are the letters SRS and CRS I see often in GDAL commands.
Right.
What do they mean? And this output here, is this a particular format that has a name?
This format is just a standard string output to std out that you can grep and do any regex implementation. So it doesn't have a name? Doesn't have a name. So here I asked for all possible things. You can say I only want the proj4 representation, and it will only give you the proj4 string. There's no standard name for this. This is just listing out all possible coordinate representations. Yeah, so each of these are standards. So this is for proj4 standard. This is the OGCWKT1 standard. So it's just labeled by the kind of representation. So you can't remember how to do the standard. But that's not well-known text we're looking at. WKT is well-known text. But that we were looking at, is that WKT right there? This section is WKT. After that, everything that follows is WKT. It depends on who created the map. So the person who created the map labels the map in different ways. So they could have created a file and labeled it with that or the next thing. They all mean the same thing. They just have different way of telling you what system they use to create the map.
Sorry. And the code for
4326?
Yeah.
So if you go online and look for epsg.io, this is essentially a website that tells you, you can type in a number there, and EPSG 4326 tells you what that coordinate system means.
Okay.
It's a standard, it's like 4326 means it's lat-lon on a WGS84 ellipsoid.
So did you?
I think that's on spatial. Oh, here. See, EPSG 4326 also could mean different things. Esri writes EPSG 432 differently, OGC writes it differently, but they all essentially mean the same thing.
But, so Gdal, the command that we run with Gdal, tell me that I can pass from one coordinate system
to the other. You can convert from one to the other.
Okay.
If you are assuming a certain representation in your code, you can use Gdal to convert the representations in your code. Yeah, if you want to reproject data, it's really helpful.
So I see well-known text 1, and there's WKT2 2015, WKT2 2018.
Yep.
Is there any significance that we need to pay attention to all these versions?
So the latest versions are more complete. So if you want to be absolutely sure, use the absolute latest version, because that goes into vertical datums and stuff as well. So this standard is evolving. WKT standard, well-known text standard, is evolving, and it's getting more and more complete. In some cases now, they're beginning to allow for axis swap, where you basically say my map is like east-north oriented differently, and you can also put that into the well-known text now, which you couldn't do earlier on. Note that this also, the same representations are used for representing vector data as well as raster data. So this is common to both types of data. If you're giving shape files, they also have a WKT associated with them. Because you get a polynomial with XY, but you don't know if the XY is lat-lon, UTM, or polar stereo. So you basically have to label those with these coordinate systems for users to be able to interpret and put on a map. This is, if you are going to ever send products to somebody else, you should label your data clearly. So this is make it a habit to make it part of your workflow. EPSG, that's the simplest that I do. Least effort is to just put the number.
And you mean by embedding this information in the graphical, the file we send off?
Yeah, the metadata.
Okay. Yeah. And Gdal will provide a way to do that?
Yes. We will look at the VRTs and show you where it is and so on. That was lat-lon. Now let's look at UTM zone 20 not. UTMs are the EPSG code block for 32601 to 32660. UTM south is 32701 to 32760. So you can do Gdal Info on 32620, and it will basically say its projection is UTM zone 20, datum WGS84. Now, somebody gave you a file, you want to know what projection it is. We did Gdal Info that gave us all these things. If you only want to know the projection and say, I only want to know the proj4 representation, you go Gdal Srs Info, output the proj4 representation of the file that you're interested in. And it'll basically spit that out. Yeah, this would be super helpful for users to have. If you are delivering files, make sure you label it so that users are able to do these things. If you want to do this programmatically, this is how you would do it. If you want to like script it up. Again, import Gdal, and OSGeo is the Open Spatial Geoconsortium. They also have a package called OSR, which is Open Spatial Reference. So you open the file, and the way you get the SRS is you call this function dataset.getProjectionRef, and that gives you the information. Then you can convert from one to other through Python functions like import from SRS, export to proj4, export to USGS, export to WKT. Those are all Python functions that you can use. So for the same file, we never build WKT by hand. We rely on Gdal. We typically label our data with EPSG code, and we say export to WKT. Otherwise, these WKT strings can get really big. So, the order can get messed up. So we just rely on Gdal to build all these WKT strings for us. Yeah.
Very basic Python question. So in order to list and see all the methods that are available for this object, you have to look at the code?
Documentation or work in IPython. So IPython basically provides tab complete. You write the object and you say tab, and it will list all the functions available for that.
Or just say print dir that object.
Or dir of the object should give you the full list. Now again, note that we can do the same thing on the GMT file as well, but this will create an error. You should see an error when you run this. That is expected. It's not a. They basically, UCSB created this nice DEM which says top corner is that number, but they didn't label it with map coordinates. They didn't tell you which projection system it is. So you will encounter data like that, but if you are to deliver data to anybody, don't do that. Label it clearly with what map projection you imply the data is on. Again, if you try to do this on one of our ICE products that we created, it should raise an error, because in radar geometry, it's not on a map. You can't say it's lat-lon. You don't have top left corner. It's not northeast oriented. This might need interferogram.turboface. Yeah. This should also raise an error. Oh, that wasn't expected. Oh no, it's working. That should raise an error. Well, that should not work. Maybe I was playing with it, or no, because it's a radar geometry file. It's not on a map. It should, and there is no. We don't label it with corners, so it should not know what projection system it is. So let's see what the problem actually is. Okay, let's look at what I did. So so the culprit, if you look at if I look at this information, is it basically gave me EPSG 4326. Is this extra line in there that in my VRT file that basically labeled it as EPSG 4326 by error. So if I were to delete this, well, it shouldn't show up there. I must be playing with something that modified it. Oh, sorry, .vrt. So
could you show them the order of the readers which it uses to check the metadata? So Gdal Info and that, because if it already works on the correlation, that makes me suggest it goes to the XML first or something like this.
Right. So one way to figure out what is happening is to set this Cpl Debug equals on. That's basically a verbose debugging statement for Gdal to see its logic of like how it's trying to figure out projection information from where. So if you happen to have projection information in multiple places, it will try to reconcile and for a more verbose way. This is how you would do it. Without the VRT? Sure, I think it'll probably go through the ICE driver and it'll probably report it. Yep, so the ICE driver assumes it's WGS84 if it doesn't find anything. So I would say when working, I tend to work with the VRT files, but in a VRT file, that's how you would label the projection system. You would have the SRS tag. And like you saw, I just used the EPSG coordinates. I didn't write out the well-known WKT, and Gdal is happy to work with that. So that's the projection system that's associated with the data model. Then you actually give user a 2D array. You need to tell them what the location on the map of a pixel is. And Gdal's convention is what we call a pixel is area. So the northernmost extent, or the 0, 0 coordinate of your 2D array, is the top left corner of your first pixel. When you ask for a subset of the array, 0, 0 represents top left. And number of pixels and number of lines represents the bottom right corner of the 2D array. It's not the center, it's the top left. That's how you index in Gdal. And a good way to confirm this is SRTM, we know, is centered on the integer lat-lon with 1 by 3600. If you run Gdal Info on the SRTM tile, it should report upper left, and you see it's not an integer. It's not an exact integer. Because the top left, the not upper left, 0, 0, is defined as the top left corner, whereas the data corresponds to center. So to put it on a map, you need to get that half pixel shift right. So it labels the top left corner by that offset, half a pixel spacing. So all the different formats, in their readers, they make this conversion so that when you query the data set with geotransform or corners, it consistently returns these information correctly of the top left corner of the first pixel. Internally, the formats themselves could be using a different conversion, but querying it with Gdal sort of makes it uniform. So let's look at the SRTM tile file name, which is how the official SRTM documentation says. This is north 33 west 119, and they say that's the bottom left pixel of your SRTM tile. So let's go look at Gdal Info for lower left. You don't see 11933. You actually see half a pixel off. SRTM in its documentation is giving you the location of the center of the pixel. But the GIS systems, so SRTM is using a convention that is called pixel is point. When the array data corresponds to the center of the pixel. This is typically what is done for DEMs. Most optical data or remote sense data use the pixel is area convention. So when you talk about, so the pixel represents everything that happened in that area. So when they talk about the northmost or the eastmost, it corresponds to the edge of the pixel, not the center of the pixel. And Gdal will do this conversion automatically to the pixel is area conversion for all data sets. So when you put them on a map, they all line up. You don't have to worry about this half pixel shifts because the data producers themselves made different assumptions.
So two quick questions. I'm looking at the geotransform thing here, and my understanding is this is going to map from pixel line coordinates onto X and Y, where X and Y are in whatever coordinate system is implicit in the file. Like this is, yes. So what if in this geotransform, G1 and G5 were negative? Then top left isn't going to be 0, 0 in PL space. Top left is going to be, you know, max P, max L.
That is correct. But we will get to it. So one really good example of this is GMT. Everybody else north up, south down. GMT does south up, north down. They do indexing from the south. Gdal hides all this in its driver implementation and consistently reports a north up information for you. So it's good for you as a user in the sanity check to make sure that the dy component, the BG5, is actually negative, so that you actually have north up imagery. It's a very common practice to have that as a sanity check when reading in the data. You query the geotransform and make sure that's negative so that you have north up data to begin with. Yeah. So the formats themselves may be storing the data this way, but the driver implementation in Gdal will still report the north up convention so that you don't have to change your code if you're using a different format. It basically adds a layer between the actual format and the consistent interface to Gdal.
So Piyush, what you explained for the SRTM is not specific to SRTM. It's for every data set, because that was just a GOT file. Right?
Exactly. It's specific. It can be any data set. It depends on the producer of the data set.
So basically, can I say Gdal assumes that whatever raster is coming in, the coordinates represent the center of the pixel, but Gdal is working with the edge, then makes the half pixel shift.
Right. So if you don't specify anything, whether it's center or edge, Gdal assumes you are labeling with the top left corner. But if you are center, you have to tell Gdal that my array is pixel is point.
Origin.
That's a metadata called area or point. But you need to tell Gdal, the default convention is you are creating data with the top left, but if you happen to create differently, you need to tell Gdal that I am on a center pixel by setting a metadata field particularly.
So I can understand how it does this. The only time I feel like this could be a problem is when you want extents of your data set. So if the top left pixel is annotated in SRTM as the center of that pixel, when Gdal has the left portion of that pixel, that's fine. But if you look at the X extent of that pixel, then the SRTM and the Gdal numbers will not match. And so if you're trying to do like a bounding box, you might get it wrong.
Let's look at the lower right or upper upper right. It actually overshoots by half a pixel. It does that conversion for you. In the Gdal Info, if you look at this upper right, it's reporting it's overshooting it by half a pixel.
So sounds like Gdal may as well just provide a conversion method. If you want to look at lat long coordinates of ij pixel, does Gdal have that function? It should. Then you don't have to worry about half pixel offset at all.
This is the equation.
Oh, Gdal pixel info.
Yes.
Then
Gdal location info will
just use that, then you don't have to worry about.
Yes.
Can either specify the lat long or the line number or column number.
Let's go back to the SoCal DEM, where we did not have a coordinate transform, but it had a geotransform. It was telling you what its left and coordinates were. Don't do that, but there are data sets you'll run into like that in real life. The way to query this geotransform, or getting the 6 numbers, which is how you convert this G0, these are indices in a 6-element array. That's called geotransform, and this is how you would convert a pixel and line location to a map coordinate. You can get those 6 numbers programmatically by asking the data sets for its geotransform. So once you have the 6 numbers, you can basically compute any pixel location with that affine transform. There are other ways of labeling. Well, looks like this might work or not work. I don't know, I've been playing with that data set. So this looks like it put the multi-look geotransform there for that. So this tells me the number of looks that was applied to that product in this case.
It's exactly 208, yes.
Yeah. Anyway, so suppose you have radar products, like we get the level 1 products from Sentinel, Cosmos SkyMed. They're not on a map, but sometimes they get annotated with what you call ground control points. These are just simple mapping of line pixel location to lat lons. They are not necessarily the most accurate way of putting data on a map, but sometimes it's provided as a convenience. I'm not going to walk through the example, but if you were to run Gdal Info on a TIFF file from Sentinel-1, you will basically see a whole GCP list that's spit out. And you will see the pixel location mapped to its lat and lon coordinates in the.
Just for the record, looks like the name of the function is Gdal Location Info.
Yes. We have examples. So then there's sub-data sets, and probably David will talk more about this in his demo. The sub-data sets, like I said, for different 2D arrays to be considered bands of the same data set, they need to be geolocated and they need to have the same size. Now, there are formats like netcdf and HDF5, which allows you to have arrays of different sizes. So you have to treat them as different data sets within a file. And, and Gdal calls this sub-data sets. So let's look at the Greenland DEM that we downloaded. If you actually run Gdal Info on the netcdf file, it basically says, I see many data sets. I don't know which one you're asking me to look at. It basically says sub-data set 1 has that name, sub-data set 2, sub-data set 3, so on. And if you want to specifically target one data set, you basically have to use this name. You're basically saying netcdf, the path to the netcdf file, and the layer you want. And then it'll behave like a standard 2D data set. Same with Srs Info. David will do more of this, so I'm just going to run through this. I'm not going to spend more time on that. And there are many other features. You can go look at their data model. I'll update the link in the notebook later today. Look at it. The other big strength of Gdal is the number of formats it supports. So you can find out what formats it supports by just running Gdal Info -- formats. There are close to 80 formats that it supports. You don't have to say, if GeoTIFF do this, if netcdf do this. You just say Gdal open, write your code. As long as it's one of those 80 formats, your code doesn't need to change. Yeah? Yes, this was contributed by folks at Grenoble. You can have data set streaming instead of actual real data sets. So another thing we will talk a little bit more about is this virtual I/O stuff. Some formats are read-only. Some formats you can create also. There are more read-only formats than create, but some support data sets. You can look into the details for formats. Another useful thing we do all the time, like I showed yesterday, is to write stats. I want to know min-max height of the DEM. You throw in the -stats flag, and it'll report the min-max medium if there's no data values in the data set. And if you actually go into the Gdal notebook, and if you look, every time you run something like stats, it creates a file called .ox.xml, where it actually saves the stats So the next time you query it, it's not going to compute the stats all over again. It has a copy of it. So next time you ask for stats, it checks if this file exists. If it exists, it's just going to report that. Otherwise, it's going to redo the computation for you. So these are useful features to have. It's just the name. It's purely tied by name, .ox.xml. Yeah, and you'll clubber it. Yeah, so the question was, how did that file know what file it's associated with? It's purely by file name association. If you had a .ox.xml and you clubber it, you overwrite it. There are other things. You can also do Gdal Info minus histogram, and it will save a crude histogram for you for future reference. So things like that, they're pretty handy. And again, demonstrating that the same thing works for different formats. You don't have to change anything. This is for the so-called DEM. Yes.
In the case when a file has multiple data subsets in it, how does one read that programmatically?
It goes to the parent file name .ox.xml, and it'll have a section called subdataset. This has the stats and. What Python? What Python do I type? The interface is the file name, so that you modify the file name by saying netcdf equal netcdf colon file name colon the layer you want to read. David will show you more. The ARIA product has more of that, and he'll walk us through.
Yeah, and on the command line, if you have one of those, it's usually, if you want to do a Gdal Info on a sub data set, you just have the file name and then a colon, and you put the name of the sub data set on there.
Like that. Yeah. So the last thing I wanted to talk about, which is probably useful going toward with the volume of data that we are running into with Sentinel and TOPS, is doing stuff on the cloud and remote servers without having to download data, and so on. Your file that you work with in Gdal doesn't need to reside on your machine. It provides interfaces to talk to remote data sets. Like what Scott showed, his VSI DEM download was talking to a data set that covered the entire globe, and he was doing subsets of it on the fly. So here is an example of us querying one tile on the open topography system that is sitting on this machine by adding VSI curl to the front of it. Since it's remote, it's going to go query it and come back, and first thing that comes back is, oh, it's a GeoTF file. Then it's going to read the header, and it's going to report exactly the same information that it was doing with a local file system. All of the Landsat data is publicly available on AWS. You can use the same mechanism to query information about a Landsat tile that's sitting on AWS. Virtual system interface, I think. And here, if you noticed, it came back with saying it's UTM zone 29, which is a projection system for Landsat. Other useful things. We often get data in zip files. We only need to read the data once. Sentinel-1 SLCs. We didn't unzip them yesterday. This is how we work with it in ICE. For example, I downloaded the dem.zip file. I'm using zip info just to list the contents of the DEM, and I see a .dem file in here. So I want to know what that file is. So here I say VSI zip, look into the zip file, and this is the path inside the zip file. Tell me what that. And it basically tells me it's a USGS DEM with that information. So I'm not cracking open the zip file.
So using this method, you can do computations on those rasters without actually unzipping them.
Yep, that's what we did in ICE TOPS app yesterday. We wrote VRT files that pointed to files within the zip file. We never cracked open the file.
So sometimes you give an input as a VRT file. Sometimes you give an input as the original file. Is there any difference?
So that's the beauty. As long as it's a GDAL compatible format, it shouldn't matter. It could be TIFF, VRT, GRD. As long as it's a GDAL compatible format, it should work.
And
all these commands should work.
And if something works, we assume that there's a associated VRT file exists?
In ICE, we create a VRT with everything. Need not be the case with other software. That was on a zip file on a local machine. You can also do this with data sitting on S3 on Google Cloud or Azure with VSI S3, VSI GS, VSI Azure. In this case, we have an example. Yeah.
So here, .dm, I was wondering where this metadata is coming from. .dm may not include that information?
I really don't know about the format. I'm just relying on GDAL to tell me that it's a USGS format and this has 4 corners. Like, I don't need to learn about the format as long as GDAL can read it.
Right.
So I don't need to know whether it's South Up or Big Endian or Little Endian. I don't need to worry about any of those. GDAL will do that conversion for me. Yes, so you see me using Gdal Info. There's the equivalent OGR info for vector data. We're not going to talk about it, but you do that on zip files and KMZs, and you can pretty much do everything you're doing with Gdal Info and OGR info. So here's an example where we query one Griffin data set with Gdal on AWS. Fingers crossed, this works. In this case, I followed the example that ASF has on its website, where I query ASF to return the credentials, and I use the credentials to query the S3 bucket. Note that we are not on AWS, so this is going to AWS making the query. If you are on AWS, this query is going to be way faster. If you're on the same cloud system as where the data is, this is going to be way faster. So right now, there is an open bug in Conda's installation of Gdal, which it's an open ticket. You see this got reported as HDF5. Hopefully, this will get resolved in a couple of weeks. They're working on it. Well, netcdf4 is HDF5, but you should see it reported as netcdf4 if you have the file locally. But David will talk more about it. Another easy way of doing it, if you don't want to query ASF for temporary credentials and do it, is to, if you have your netrc file set up correctly, then you should just be able to do this. From your netrc, it's going to go get cookies from URS.earth data, and it's going to be able to talk to data that's sitting on S3. There are times when you use one particular data set extensively. You don't want to go read from the file all the time. You can make an in-memory copy of it with VSI mem. So in this case, we create a dummy file name which doesn't exist on disk, but it will, for all practical purposes, behave like a Gdal data set, into which I'll load a data set that I'll use again and again. And I can continue working with it with the same Gdal interface as an actual diskon file or an actual file that's sitting on S3. So this is useful when you're writing applications where you're using one database to look up different things, and you have that sitting in memory. Sorry, I'm running a little behind. Maybe I should speed up a little bit. The next thing I want to talk about is this VRT business that we've been talking about. It's called the virtual raster table format. It's very specific to Gdal, and then other people are beginning to support it. So here is an example of a burst.slc.vrt from yesterday. You see, the VRT data set basically says it's a size 20,000 pixels, and 1400 lines of type cfloat32. And this is a simple source. It points to a zip file sitting somewhere with a TIFF inside it. So that's a zip file for a Sentinel-1 product, where I say the source file has one band. If you don't specify it, it will go query it and get it so that that can put a little overhead. Then you have the source properties, which basically, again, it'll go query it if you don't provide it. And it says the data type is C in 16. That's what Sentinel-1 distributes it as. But our code reads it as cfloat32, so this inherently does the conversion. I don't have to do anything. And here it says this rectangle in that TIFF file inside that zip file corresponds to this rectangle of my burst. So you just purely metadata labeling it and not actually extracting files out. This is what we were doing yesterday when we pre-processed the top SAP. I've basically gone through the burst and sort of annotated it for your information on what exactly happens, what each piece of information is. For example, VRTs are also helpful if you want to change metadata of a file but don't want to copy the whole data set over. You remember the SoCal DEM, which did not have a coordinate system information? What I'm going to do now is basically say, convert it to a VRT and assign it a coordinate system. And basically, this does not create a new file, but if you look at the new VRT, basically looks like this. It's a size 1201. That's the coordinate system. That's the geotransform. It has metadata. It pulled in the metadata from the GRD, and it basically says, oh, this is the source file. That's the rectangle mapping to it. And if you query the new VRT, it will also report the coordinate information for you. You did not have to copy over a big data set and relay change things in it. You just do it via the VRT. And if you query it, it's going to do the same. It's going to report, behave just like another GDAL data set. The best application is what Scott showed yesterday for the global SRTM VRT. That is the URL for all of SRTM VRT. So if you just want a DEM in some place, you just go crop it, and you never have to have the DEM sitting on your machine. And if you do Gdal Info on this, it's basically going to say, okay, that's virtual raster. It talks to all these different files. It takes a bit to run to list all the files. You can also suppress the printing.
Yeah, so because I have the full URL in that VRT, you can actually download that VRT to your local machine, and then you could do like a GDAL warp and say, I only want this stuff in UTM.
Yeah.
So you could just have this VRT that mapped that one into UTM, and now whenever you call Gdal Info or Gdal Translate, you call it that new VRT that you've defined, and I mean, that VRT is like 5 megabytes or something.
Yeah, it's tiny.
Created 5 megabytes of disk space to have the entire SRTM and UTM.
Question?
So if I have Python code that's using Gdal to open files, I could open a VRT, and the VRT could point to something somewhere else. So I could run ICE, which I use the Gdal, and never have the SLC zip files locally.
Yep.
I mean, it'd take a while, but
all you have to do is in the file name in the input XML file, you have to say VSI S3 or VSI GS or whatever.
So using the VRT of the global SRTM, can we create a VRT of area of interest and then drag and drop that VRT to QGIS and load it up?
Yes. So if you are on a fast enough network, it will work.
It would download only relevant. Okay, it's beautiful.
If you looked at Alex Gardner's new products, all the data is sitting on the cloud, and he's putting out whole continent-wide Antarctica, Greenland maps this way. just VRTs, text files. You drop it into QGIS and you scroll around like it's live data. And it's actually pulling it from the cloud on the fly. Here's where probably like it's a radar engineer thing. If you want to create amplitude, I don't want to take my complex data, create another big file of like absolute value of the data, or the arctangent of the data, or the real part of the data, or the imaginary part of the data. VRTs allows you to do these things called pixel functions. You just write a VRT, point to the source, and say, I want that data in magnitude or dB or whatever. You never have to create a big-sized file again. The VRT will do that conversion for you on the fly. So that's the other useful thing. This was contributed by Antonio Valentino, who does a lot of work on Cosmos SkyMed. So it's like there's more and more radar relevant stuff coming in. So another reason to use Gdal.
Can you also measure things in Gdal? I mean, like if you knew the length and width of something and you wanted to render it, I guess maybe I'm not sure I'm asking the question right. I guess can it do ground to image coordinate translation also? Can it do
We
that?
will talk about it in a separate notebook called projections. Maybe bring that up again and we can talk about it.
You can also do calculate distances between points and stuff, but that's more in the OGR because vectors.
All right, so that was the intro. Sorry, went over. We'll let David talk about how it's relevant for the unwrapped product, then we'll come back to actually manipulating data with Gdal. You want to take one? Are we going to take a break? Okay, sorry. I'm over by half an hour. So 10-minute break. Does that work? We'll be back at 10:45. Yeah.
Yeah. Okay. So let's continue. I'm back in a weird language apparently. Let me close that. So we're going to continue with Gdal, but now we're going to demonstrate this on the area product. So we have shown you examples on how to run tops with ICE. So the area standard product is actually the output from ICE, but it's all packaged in this netcdf format. So we will really go into detail tomorrow on how we got to the idea on which is the number of looks, how we packaged it up, etc. But currently, we're just going to demonstrate you how you can use Gdal with all this functionality of these different readers, how to access different sub-data sets within a netcdf file. So first of all, let's go and copy the notebook. It's again moving your work directory. So you can now do copy minus recursively. Again, the notebooks are in the share folder under notebooks. You have the Gdal folder, and I think it's 02 area GDAL Basics. So copy that into your workspace, and then you can go and open up the notebook. So this notebook was put together by Emre, who is a postdoc at JPL. So we will go over an example on so in this notebook, there's a couple of things that you will be showing. So you can use, as Pierre showed, you can use Gdal on command line. You can use it in C code. You can use it in Python. So in this notebook, we're not leveraging anything from area tools yet. We're only leveraging Gdal, and we will give you each time two examples: the example from the command line and the example on how you would do it in the Python way. So the first thing is for you to set up the notebook. That is just us setting up the directory structure, making sure you're running it at the right location, and making any folders which you might not yet have. So execute that first, and you can see this should be roughly your work location. In terms of the data set which we are going to be using, we're going to be looking on track 77 from Sentinel.
So that's actually the track adjacent to track 4, which we were talking about this morning. And we're going to look on a single product, which is on the US-Canadian border near Lake Erie. So that is Lake Erie is up here. So we're going to be looking over this area here with an interferogram processed using TopSap, like you all did yesterday, but then packaged in this NetCDF format. So that's what you can see here. There's a little bit of background on this NetCDF packaging. So we have both metadata layers, which is our baseline information. It's our incidence angle, it's our azimuth angle, etc. All with their own sign convention, which are on the website. So they might not be the same which you're used to. So it's always key to go and look back onto these. The other thing is it has a dataset layers. These dataset layers are full resolution. The metadata is not at full resolution. So we will really go into why and how you can use this tomorrow in detail. So there's multiple download options for downloading these standard products. This morning we used the area download command. You can actually also just go to the ASF website, download it through the Vertex page. We will give a demo on that tomorrow as well. The other thing is, if you know the product file name, you can always generate the URL to download the product. So the first URL is always static. So it's getting ready for NISAR, Alaska, the door. So I guess that's why we need getting ready for NISAR here. And then download. So that is kind of a static URL, and you can just directly provide with the product ID behind it. And that URL will resolve where the product is stored in AWS, and then we'll actually download it for you. So you could actually click on that, and it will go into your regular download browser. The other option which you could do is you could go to the area products page. We will go into detail of that later on, or you can just use our area download command again, and that's what we're going to be doing over here. So I already specified the bounding box really narrowly over that area, so it's only going to find one frame, and then I'm explicitly asking for a single interferogram to be downloaded into the data dir. So in the data dir, it is just called, if you look up, it is just called product, and that's actually the default. So you can go and execute that cell. It might ask for your password. That means that that bulk download cookie has expired. So you would just need to go to the terminal and do it again. If it is not yet expired, you would just see the download to be starting and going into that products folder.
David, just as an experiment, if going back to the last talk, could you, instead of download it, could you just link it with the VRT, and we'll do all the same things?
Correct. Yeah. So Piyush was figuring that out for his notebook. So he put a note on our GitHub page I opened it up as something which we wanted to know, and Piyush was experimenting with that. So he put all the details on our ticket. So I haven't really played with it myself, but that would be another way of directly using these products for this notebook and use the VSI command instead. Yeah. Sorry?
Yeah, I was asking if you had to have authentication. So VSI curl might actually be.
So VSI curl, Piyush, you need to set a set of paths and environment variables, which
set Gdal HTTP cookies environment to point to a file to say Gdal use these cookies every time you go. And do that.
Is everybody able to get the product? No? So what problem are you having?
You may need to log in and agree to a EULA. So go to urs.data.nasa.gov.
Okay, and you have the same problem?
Look for Griffin, GRFN. Search for GRFN.
Okay, so normally if you were able to download this morning, you should be able to download now as well. Yeah, except, could you assist them? I don't think they were able to download it. Okay, so let's go and retrieve information. We have a question. Give me a second.
Anybody else who's having access issues?
Okay. So Can you show me? Okay. So whenever your username and password is required, go and open up a terminal and copy the exact download command. Go back to the folder where you have copied it in. Give me a second. So if you're having request for a password, go into your workspace, go into the area Gdal Basics folder where you have the notebook, and then run the command directly. So, sorry? Give me 1 second. So if you are having authentication requests, Jupyter is not interactive. So go to your notebook. So you should not do count. So make sure you're running the right command, like up here. So in the Gdal basic notebook for area, we're downloading this product over here. So it is already different from the URL which you're using, and it doesn't have the count option as output. It's actually, if you don't specify anything, it will download. So with count, it will just say there is one product found, and you don't need to provide your password. So now, if you specify this one, and then press enter, it will ask you for your password and username, and just type it in. So once you have that cookie, as long as it's not expired, you can reuse it. Once it is expired, you will need to go into the terminal and do it. Okay.
Anybody else having download problems?
Okay, so Piyush will go around, and if people have down.
So people are seeing errors, skipping download. See the line above, it says file already exists, so skipping download. It means you already have the file.
Okay.
Don't read it as an error message.
Okay. So everybody has a file? We're good? Okay, so let's go and retrieve information on the product content. Similar to what Piyush was doing before, you can retrieve the information. So in the Pythonic way, you would open up the file. So the file name we just hard-coded at the top. So you open it with Gdal. It already knows. It will figure out what type of product it is and which reader to use. So it will be using the netcdf reader. And then you can actually get the information on the data sets contained by doing Gdal Info and printing that information out. And at the end, we just close the data set again. So you can run those two cells, and it will print out all the information which you can find. So I will explain you now rather than later on what the interpretation is. So you can see here at the top, it finds the driver to be the netcdf driver. If this would be ever showing to you the HDF5 driver, you're not using a recent version of Gdal. Our products are only supported in Gdal 3 and above. That was something which was contributed by Julien Demer in France. So the other thing which you can see, you first see all the global variables. You can see some different layer types. You see bounding boxes. And then if you go deeper, you can start to see sub-data sets. These sub-data sets are the data sets which we're using. You can see a product bounding box. You can see unwrapped phase, which is in a science, grids, data, unwrapped phase group. You can see similar for coherence. It's in the same data folder. If you go further down, you would actually start to see a change in structure. Here's an imaging geometry folder where you have the perpendicular, parallel baselines, etc. So you can see this netcdf, it's not a single data set. It is like you said, you can use these different rasters within the same data set. And here we actually have on top of that different file structure for each of these data sets. So they're if you would think about in a browser, go like the good old Windows computer, you would open up a folder. There's 3 different subfolders in there. One folder here is called grids. Then it has a subfolder imaging geometry. Actually, if you look above, there would be a neighboring a neighboring folder which would be at the same level, which is data, etc. So think about it as a directory structure. As you can see, it reports here you these coordinates. This doesn't have really any meaning at this point because Gdal just looks at the top file. It doesn't give you the information yet for a sub-data set. So you can, at this point, you can just ignore that. Later on, I will show you how to retrieve the actual projection transformation information for a sub-data set. So that's the next section. So this is the Pythonic way of doing it. If you want to do the Gdal command line way, you would just go to the next cell and you use Gdal Info. Again, you just specify the netcdf file, which we currently have downloaded in products, and we're using this file here. So you can execute the cell. It's going to give you exactly the same information, but now at least you're using the command line interface. So again, the global variables, you see these sub-data sets. It's identical to what you see in the Python version. So interpretation, you can read through it, but it's kind of what I have been explaining above with these different data sets, these different folder structure, etc. So now let's go and access one of those data sets. So that's called a sub-data set. So you can go and execute it. There's, again, two ways to do this, Pythonic way and the command line way. So a key thing is what you should know is that whenever you see here all these different folder structure, if you would ever want to do it yourself for a different variable, what you would need to copy is exactly one of these lines, including the netcdf in front of it. So this is telling Gdal, use the netcdf driver, and then go and open up this file and go into this folder structure to find the connected component data set or sub-data set. So if you go down for this example, we're opening the unwrapped phase here. So we say it's a netcdf file. We give our file path and file name, and then we point to this unwrapped phase. And then we're just going to retrieve the variable and print it out. So now you can see it starts directly with specifying what is my projection, what is my transformation. So you see this is actually similar to the, it's in long lat, it's a WGS type of projection. It's the general EPSG code for long lat. And then in addition, what you can see here, if you go down, you can start to see specifications to the unwrapped phase itself. So at the bottom, you can see, for example, the fill value, which is a no data value for a netcdf. That is already embedded in the product. You can see the units. You can see the standard name. So with this netcdf, when we package in TOPS was its kind of own specific ICE format. By going in netcdf, we kind of made it for the user no longer dependent on an InSAR processor. Actually, it also became SAR sensor neutral. The key thing is what we're doing, we're using netcdf, but we're enforcing CF compliance. So that's the climate and forecasting conventions, and they generally work on the globe. So they want to know exactly where the projection is, what the transformation is, that they can change that. So we're enforcing that the same for each of our data sets. So that's the strength now, that you can directly extract these data sets, do a Gdal translate, do a crop, do a merge, mosaic things together at once. The other strength is that we're forcing all these fill values with the data itself. So if you do, for example, a Gdal Statistics, the no data is taken into account and it will only use valid data points. So in terms of getting the statistics, we already had the file open, so we retrieved the unwrapped phase directly. So now we can just do unwrapped phase, get the first raster band. There's only one raster band in there. And then say, get us the statistics. So if we do that, and generally it always spits out some red 2 on the first attempt. But that's okay, it's just a warning. But you can see the minimum of the unwrapped phase is -35. The units are, anybody? Radians, correct. And you can also get the standard deviation, the mean and the max. So that's an easy way of retrieving that. Any questions so far? Then we have exactly the same command line equivalent. We're going to now run that one. So you can see Gdal Info. We specify again netcdf driver, the product file name, and then we're going to go into the folder structure saying we want to have unwrapped phase to get the information here. So that's going to give you exactly the same copy which we had above before. And it provides you again with the no data value. Piyush mentioned before that when you have run the stats, it's actually embedded in the metadata file. So now you can see that the stats are automatically shown as well. If you would have not run the stats, it would only show the information which you would have known at that time. Now, you can still run the stats also from command line. So how you would do that is you would still have your same Gdal Info command line, but then you add -stats. So very, very straightforward. You can see that it will run way faster now, because now it is just reading it from the metadata. It's actually no longer calculating it. So, and again, that is being provided here at the bottom. So you can see from something else in here that the projection is being provided. Let's see. So you can see the EPSG codes to change depending on the ellipsoidal, etc. But generally, the EPSG code is provided over here, the final authority. So that's 4,326. So it's similar to Piyush. You can retrieve that. What does that mean? Using the Gdal Srs Info. So you can see that all these products are provided as a long lat projection with respect to WGS 84. Any questions so far? We're just using Gdal manipulating this product. Okay, so now let's try to load these products in Python and make a map out of that. So that you can only do in Python, of course. So if we go and load the data set, again, we're going to retrieve the unwrapped phase. We're going to read the data now. So we say get raster bands and read the array. And we just store that as unwrapped data. By default, this is a NumPy array of data. And we will just report out the size of this array. So it has 2,246 by 4,232 lines and pixels. The next thing which we can retrieve is the projection and the transformation. We already know it's in long lat information, but by using the transformation, you will get the upper left longitude. You will get the sampling of the longitude. You will get the same thing for the latitudes. So you can reconstruct the mesh of the data being used. And that's what we will do in this cell over here. So we retrieve the projection. We actually, this is, I don't think you need to do this. This is just for ourselves to debug. But you can retrieve the unwrapped phase, the geotransform. And the geotransform is this long, delta long, is the lat, delta lat, and this Q is generally 0 for our product.
Question.
Yes.
So get raster band and read array, to me, sounds redundant. If you don't read array, what do you get?
You will just get the object.
Object.
Raster band is its own thing with its own information. The data it owns other things besides the data. So you have to explicitly ask it to read as an array.
So think about the no data value would be contained within the bands. The projection would be contained within the bands, but it also contains the data, which is the raster array.
When you get a data set, it's still a GDAL object. When you read the array, it's now a NumPy object, and you can start doing computations.
Yeah, and when you say get raster band 1, it hasn't loaded your multi-gigabyte data set yet. It's just ready to go fetch it when you ask for it. Nothing gets loaded till you ask it to load it.
Mm-hmm. So we can run the command here, and we just try to reconstruct it ourselves. What the different information is, and you can see this is exactly the same with what we provided above here in terms of the coordinates over here. See upper left, center, lower right. So we were just reconstructing that for fixing the axis later on in the figure. So the other thing is what we're now going to do, and this goes back to Sang-Ho's question. So you see we have this raster band. Now we're going to retrieve the no data value because we want to mask out anything which is no data. So we retrieve the no data value by using get no data on top of the raster band. We close now the data set. We no longer need it. And we're going to use that to mask it out. Now, we will go into details on what is the best practices of standard product later on, but generally we provide a metric with unwrapped face as well on the confidence, which is called the connected component, and Harish talked about that a little bit before, and we looked at this for the Kurdistan earthquake. Do we have a lot of connected components or not? Generally, connected component 0 is where snafu doesn't know what to do with it. Maps to water, maps to decorrelated areas. So we're on top of that going to load the connected component and mask at connected component 0. And the reason why we do that is we're going to be looking at a scene which covers Lake Ernie, so we want to get rid of the water while not downloading a water mask. So we're also going to load now the connected components, which is in the same folder, and we're just going to read the array, and we're going to close the file again. And what we're now going to do is we're going to mask the array wherever we have no data, and we're going to mask the array wherever we have connected component 0. So that's being done over here. Then we use Cartopy. That's another package similar to Basemap, Matplotlib, where you can generate maps with. It looks very much like a GIS map, so we will run the command just to make the figure. And I think this is kind of new to me in terms of using Cartopy. It's the first time that I actually use it. But I kind of like the background with the map behind it. And you can see now the water is generally being masked out. It's not yet ideal. If you really want to mask it out accurately, use a water mask instead. But you can see that the unwrapped face varies between 0 to about 12 radians. So this is C-band. So does anybody know roughly how much centimeters we are talking about? 5? Yeah. So 2 pi corresponds to half a wavelength, so that's about 2.6. So if you have double the amount, we have about a wavelength of displacement. That's correct. Then the last one, that's kind of again Gdal and Python version, is how to crop these different data sets and make a KMZ file out of them. So within Python, you would actually again open up the data set. So we open up the unwrapped face, and we're going to be doing Gdal translate on that data set. So we're actually going to provide it the option to say OF stands for output format. We're going to make a KML super overlay. We're going to scale the data set. So by default, it's a PNG. It has a dynamic range of 0 to 256. So we need to scale our data values within that valid range. So that is what the minus scale option does. And then we also say, please provide us with a PNG as output format. And then these are just the options. Here we're really going to execute it to generate the KMZ file. And then we close again the data set on its own. So you can run that as well. We don't have Google Earth as part of Jupyter Hub. So you can go into the browser and just download the KMZ by clicking right and open it on your laptop if you have Google Earth. But alternatively, we also make a figure over here to show it later on how it looks like. So the other way is to do it on the Gdal command line. So that you similarly use Gdal translate. You specify the same options, you scale it, and then you specify the input data set, and at the end you specify the output data set. So you generally see those dots, which is just telling you how it is processing. And you might have seen this a lot in ICE as well, because ICE uses a lot of this as its backbone in the processing. Okay, so you might have the same question now. How do I crop it to my area of interest? You can just provide the projection window, which would then limit it to this region. So we're talking about longitudes, so west, north, east, south. So you would just provide that over there. You can execute that cell. That's just going to give you a cropped KMZ. Should be faster because it's smaller. And then if you would visualize them, this is what you would get over here. So you can see in the KMZ, we didn't specify anything about no data, so the water is still there. There would be other ways to probably mask that, but you might need to default to a different output type. I don't think PNG handles transparency. I think it might need to be an EPSG or JPEG. Yeah. So this is the basic way using Gdal to manipulate some of these NetCDF products. Any questions? Piyush, do you have the mic?
So when we masked out those areas, no data value and the connected components, field value 999999. So you replaced those pixels with 99999?
Yes, we were doing that over. Where were we doing that? Here.
So that new value 999999 was understood as transparent in what line in the following code?
So I think because it is a NumPy masked array, it already has the information on what is the mask value and what is not. So I think you can put that to any value because it's a special NumPy array. So it's not a NumPy array default, it's a NumPy array masked type. So it already knows just by, it has its metadata embedded in it on what the no data value is. So I don't think you need to specify it anymore in Cartopy whenever you're going to go and plot it in there.
So 99999 is something special?
No, you could use anything. I just didn't want to use, or we didn't want to use anything which is in the valid range of data. So we know. Oh, yeah. Oh.
Okay. So field value has to be just outside of.
Yes, I mean, I would do it. I mean, so the chance that you're going to hit exactly that value is kind of small, but I think it would be good practice not to take it in your valid data range.
Can you say nan, not a number?
I think as long as it's a NumPy nan, it's okay. I think. Any other questions? Then I had to give the floor back to Piyush.
We'll see a lot more of this tomorrow for the time series.